One of my favorite things in mathematics is something called the Pascal's triangle, a very interesting formation of numbers which lead us to many interesting facts. Let's first understand what the Pascal's triangle is. We start with the number 1 and we write the two numbers 1 and 1. Well, these are the only three things that you have to remember. Now, let's see how the triangle gets formed. Every time you start the next row, you start with the number 1. Then you add up the two numbers which are above. So 1 plus 1 and you write 2 and you end the row with 1. Let's repeat the process. 1, 1 plus 2 is 3, 2 plus 1 is 3, again a 1. 1, 1 plus 3 is 4, 3 plus 3 is 6, 3 plus 1 is 4 and 1. 1, 1 plus 4 is 5, 4 plus is 10, plus 10, 4 plus 1 is 5 and 1. And I can keep on continuing. Now this arrangement of numbers is known as the Pascal's triangle. Why is this triangle very interesting? Well, let's do some quick observations. The number 11 is actually very closely related to this particular triangle. If you see the value of 11 to the power 0, then that is the first number in the triangle, that is 1. 11 to the power 1 is 11, 1 and 1. 11 square is 121. 11 cube is 1331. 11 raised to the power 4 is 14,641. But is 11 to the power 5 15101051? No. Then does the Pascal's triangle break down here? Well, let's actually see what the value should be. So 11 to the power 5 is 11 to the power 4 multiplied by 11. So 14641 multiplied by 11. So 14641, 14641. I should get 15061. So this number should read 161051. Let's see. So I put down the 1, the 5. For 10, I put down the units place and carry the 1. So 10 plus 1, 11. So 1 and 1 carry forward. 1 plus 5, 6 and 1. Voila. So the number 161051, which is supposed to be the value for 11 to the power 5, absolutely continues the trend. So each value, each row in Pascal's triangle is nothing but the successive powers of 11. But that's not all to it. In fact, I have used Pascal's triangle to a great advantage for something called the binomial theorem, right? Identities and binomial theorem. Forget the binomial theorem part. Identities, what are they? Well, if you remember, then a plus b, the whole to the power 1 is a plus b. A plus b, the whole square is a square plus 2ab plus b square. A plus b, the whole cube is a cube plus 3a square b plus 3ab square plus b cube. To continue, in fact, to go before, a plus b the whole raised to the power 0, anything raised to the power 0 is 1. If you observe closely the coefficients of each of the variable. So in the first one, the only number was 1. For a plus b whole raised to 1, the coefficients are 1 and 1. For a plus b the whole square, my coefficients are 1, 2 and 1. For a plus b the whole cube, my coefficients are 1, 3, 3 and 1. Lo and behold, Pascal's triangle starts appearing, right? So using this funda, can I find out what can be the value of a plus b the whole raised to 4? Well, coefficients are easy, 1, 4, 6, 4 and 1. So my coefficients will be 1, 4, 6, 4 and 1. But what about the terms a and b? Well, if I observe, then a cube, a square, a nothing, b cube, b square, b nothing. The powers of a are decreasing and for b increasing. So fourth power, so a power 4, a cube, a square, a nothing, b power 4, b cube, b square, b nothing, and put the plus signs in between. So a plus b the whole raised to 4 is a raised to power 4 plus 4a cube b plus 6a square b square plus 4ab cube plus b to the power 4. And that is how I have used the Pascal's triangle to often work out the identities. Do you know any more interesting things which can be derived from the Pascal's triangle? If yes, do drop a comment below.